Okay, so we'll continue with the talks of the second part of the morning. Now we start with the talks of for 20 minutes. So I remind the speakers kindly to try to keep it around 18 minutes, so we have a few questions at the end. Um, so now we have the pleasure of having Professor George Welch, who is presenting
Okay,
his first.
thank you very much. Thanks for coming in. I know everybody would rather be drinking coffee. I'll have to rush because I want to get through the physics and have time to make fun of Dan at the end. But this is going to be real different kind of physics from what Professor Kleppner has done most of his career, so we'll have a bit of an introduction, but I also want to talk about some of the wonderful people that I've had a chance to work with at Texas A&M University. It's a hot place in the middle of Texas. You should all come and visit. We have beautiful buildings, lots of wonderful physics. I've been lucky enough to work with several wonderful colleagues. Professor Marlon Scully and I have collaborated for several decades there. Alexei Sokolov and Yan Lane are other professors in the department. Shi Wang, Yao Chanji, Kai Wang, and Dmitry Pestov are former grad students that did practically most of this work. So a little bit of outline. I probably should just skip it so I can go right to the thing that I want to talk to you about, and that's vibrational absorption in molecules. So in order to be very simple, we'll think of a molecule as just a couple of atoms connected together by a spring. Dan Kleppner told us that hydrogen is the proper study of man because it's the simplest atom there is. Well, the simplest molecule is two atoms stuck together, and of course that's, an atom with one atom too many. But molecules typically have vibrational levels that are separated by something on the order of 1,000 wave numbers, and the spectrum of those vibrational levels has often been referred to as a fingerprint of various molecules. So techniques to go in and measure vibrational absorption are very important because they allow you to identify species of molecules. One way that that's often done is with inelastic scattering. And I don't want to go into this too much, but it's just a little bit of things to remind you what's been said before. If you have a molecule, an incident field will induce dipole moment. And the polarizability of such a system can depend on the nuclear spacing. So that's all you need to know. So if you've got a molecular vibrational frequency, so I'm saying that the separation between the atoms vibrates at some molecular vibrational frequency, something you might want to see, and you apply an incident field, then what you get is you get two things that are both oscillating. So you get a product of the molecular frequency and the optical frequency, and of course that means sum and difference frequencies. So inelastic scattering is like that, and of course you all call this the Raman effect, and Raman got the Nobel Prize in Physics in 1930 for this. What a lot of people don't realize is that on the other side of the Iron Curtain, Leonid Mandelstam actually saw it first and didn't publish in journals that are accessible to people in the West, so he didn't get the Nobel Prize. A lot of people don't. So these is a more quantum mechanical way of looking at this Raman scattering. Now, coherent Raman scattering is something that can be much more useful, and then again, not much more useful. If you can use a pair of lasers to get a molecule vibrating, then you can scatter a laser off, and if your initial lasers get a huge sample of molecules vibrating, then all of the inelastic scattering will be in phase. And of course, then it's an n-squared process instead of n, and that can be very powerful. So that is, in fact, called coherent Raman scattering, or CARS. And many of you have heard of CARS. Not everyone knows that CARS was first observed at the Ford Motor Company. One of those cute little facts in physics. Unfortunately, Terhune and Maker didn't name it coherent anti-Stokes Raman scattering, or CARS. It wasn't for 10 years until Begley at Stanford actually coined the name CARS. But still, CARS was first observed at a car company, something that's great. The you know, cars can be very powerful. You get this n squared, but it also is not, it has a lot of drawbacks. And the most common cited drawback is that if you have levels in resonance for doing this coherent inelastic scattering, all you got to do is reorder these fields and you get 4-wave mixing. And you see this process just add up 2 photons up, 2 photons down. It's not sensitive to the vibrational spacing. That's total background. And this process then can completely mask this process. And for 1,000 years, not 1,000 years, but for decades, people have done heroic work to find a way to suppress 4-wave mixing in order to see cars. And that's kind of, in many ways, the name of the game. In our group at Texas A&M, we've worked on that as well. Now, I want to tell you about another problem that some people consider a problem with cars that'll get to the kind of the point of the talk, and that's line shape distortion. Now, I have a few equations that I have to go through too fast, but you'll see the point of this, which is that the car's polarizability, it can easily be estimated, and I've taken the susceptibility and divided it into 2 parts. So look inside these parentheses. I've got a background and then something I called chi sub r, which would be the species I want to detect, the stuff that I want to see. Okay? So this is what I'm interested in, this is background, and I write my little n in front just to emphasize, oh, I'm trying to detect maybe the density of this Raman species. Well, the problem, though, is measured signals proportional to the polarization squared. So you get this, which I want to see, that's the signal I'm after, but I've got this. I've got a big background, and I've got this interference term. And this interference term between the background polarizability and the Raman polarizability gives you a distortion of the line shape. And that means it can be hard to find the center of a line when the line shape is distorted in a way that depends on density of species and everything else. Okay, so that's what I want to say. In particular, the phase of the background may be approximately constant, but the phase of a resonance that you want to see varies by pi when you tune through a resonance line. So this is going to mean that at some frequencies, interference between signal and background is constructive, and at other frequencies, it's destructive. A way to try to get around that has to do there are many ways to try to get around that. One of the things, we've done 2 approaches in our lab. So this is kind of a complicated experimental setup, but the crux, the thing that you should think about is pulse shaping. So what we've done is take these 3 lasers that have to be applied to the molecules and make 2 of those lasers be ultra fast, femtosecond lasers. So think of these first 2 lasers as really short pulses in the time domain, maybe 50 femtoseconds, maybe 30 femtoseconds, and our third pulse we shape. In particular, we shape it so it doesn't have any amplitude while the first 2 lasers are on. And that means you don't get 4-wave mixing. It requires all of the lasers to be on at the same time. And this technique kind of avoids that. So the first 2 fields hit a sample of molecules, get them vibrating, and as long as the vibrational time is long enough, you can then wait till the light's off, then put on a probe field and probe that vibration and get a huge coherent scattering off the entire sample of molecules. And that sort of pulse shaping works very well, and a lot of work has been done with that. But it doesn't address the line shape distortion. For line shape distortion, heterodyne is a way to get around it. And I don't want to go through all the details of these slides because I don't think that you'll care too much, but let me just show you what I'm talking about. So again, it kind of looks like a complicated picture, but I take these femtosecond lasers that I was going to shine on a sample. So here's a Raman sample. And before I do that, split some off and send it through a non-resonant sample. This could just be water. If you've got some molecule you want to detect and it's generating background and the background is going to interfere with the signal and produce line shape distortion, this might seem like a crazy idea. Why am I going to take and produce even more background light and mix it in? Well, the reason is because of interference. I can use that to cancel this background. And you can write down what your signal is, and you get a combination of the background signal and this Raman active stuff that we want to see, and cosine and sine of some phase angle that you can adjust interferometrically by moving mirrors. And moving mirrors is easy. We all know how to do that. So that works really well. It lets you even isolate the real and imaginary parts of the Raman susceptibility, and you can then pull out lines. And these are data taken in methanol, where there's only a single Raman line. But what we've been able to do is the red curve shows purely the imaginary part of the susceptibility with no background interference. So it's got a nice Lorentzian line shape, and I think that's pretty cool. Because it's a heterodyne type technique, you can also get amplification. This is a line-shaped distorted signal. If you look at this little inset, you see the line shape is kind of crazy. It goes down, it quickly goes up, it tries to go down again. So it's really a distorted line shape. And in some arbitrary experimental units, it's about 500 counts. When mixed with our local oscillator, we get something more like 10,000 counts. So that's a heterodyne amplification of a factor of 20, which is very good for looking at weak signals. So both things are present in the heterodyne experiment. The ability to interferometrically cancel the background and the ability to amplify. Now, I'm probably running real low on time. We'll make it. You can do more, and this is what I think is cool. So it's a cool little result. I don't know if this will ever be practical, but physics is often about things being fun. Here's what we found. This is this time domain picture I showed. 2 lasers that are ultra-short pulses, and then a shaped pulse that doesn't overlap. Well, actually, it does overlap. You can never make things go to 0. So I've tried to schematically illustrate. There's always down here a little bit of overlap. You never make the pulse go exactly to 0. And that sounds like that would be a problem and lead to some residual background effects, and it does. And we started playing around with that. One of the things we noticed was if you make the signals that you're looking for really small, like you're trying to do trace detection of a molecule where there's not much there, then even this residual background can be so big that you can get signals that are proportional to density instead of density squared. And it led us to thinking, and we played around and we found something new. Okay, now let me then just have a look at this pulse shaper, because we don't have huge amounts of money. This is a homemade 4F type pulse shaper where you take a broadband laser, split it into its constituent frequencies, divide a little bit out, and recombine them, and you get this sync squared shaped pulse. That means in the time domain, I mean, this is sort of intensity. The field is actually changing sign. So look at this green curve. That's like schematically illustrating the electric field of the probe pulse. The phase changes by pi there. The phase of the background is nearly constant. And that potentially is very useful. So here I'm showing the decay of the vibrational coherence and some kind of signal that we might want to measure as a function of time. And you can write down what that signal is, and I've done a trick. I've taken the background and separated it into its amplitude, that's what the vertical bars mean, and phase. So the question then is, how can we control the phase of the background? And there's a cute trick for doing that. You might think the background is just going to be there, but think about what happens when you have an asymmetric pulse, not a Gaussian pulse, an asymmetric pulse. And I've simulated that by having a Gaussian pulse on one side and a hyper-Gaussian on the other. This is just math. It's an asymmetric pulse. And if you Fourier transform it into the time domain, you see you don't get a 0. It's not quite sync squared. The reason for that is that the real part changes sign, but the imaginary part doesn't. So the intensity doesn't go to 0, and the phase changes by pi. And it's just what we need. I'm just showing all of that in one slide. This is real and imaginary parts, amplitude and phase, Amplitude doesn't quite go through 0, but the phase changes by pi. So that means, and now I'm showing minus pi the other way, it means that instead of trying to do it right, if you actually go and mess your experiment up, so we put a knife edge in and deliberately created an asymmetric pulse, then we will have background that's non-zero, but whose phase changes in a way we can go in and explore. And we've done that, taken a lot of data. This is just an example showing how these line shapes change as you adjust delays. And by looking at just the right place, you can go in and pull out the real and imaginary parts of the Raman susceptibility. And this data shows that the magenta curve is exactly the imaginary part of the Raman susceptibility in methanol, a single line taken with the car's heterodyne signal, but the local oscillator in the heterodyne is the background generated by the molecules. So there's no interferometer. It's really kind of cool. You actually do heterodyne detection, but your local oscillator is generated by the molecules that are surrounding the ones that you want to see. And that gives you amplification. It lets you adjust the phase, go in and check and pull out signals that you want. It may not ever be practical in a real situation, but I think it's awfully cool. It's very seldom that you get heterodyne detection where your local oscillator is generated by the medium that you're probing. So that's the result. Here are the conclusions, basically what I just told you. And since I'm so short, I don't want to read it. Instead, I want to ask, what has any of this got to do with Dan Kleppner? And the answer, I don't want to sit here and lie to you, is maybe not really very much. However, Dan taught me laser spectroscopy. So that's really the kind of the connection. I learned how to do stuff. Our experiments back in the old days looked a whole lot like this. This is femtosecond lasers. These are motorized delay stages doing what I just described. But, you know, if you only glance at an experiment, it kind of looks the same. I used the same techniques that I learned 30 years ago. And not only laser spectroscopy, but also how to write, how to teach, and to love physics. I think many, many other students got that from Professor Kleppner. But now I have to tell you an anecdote. I also learned laws of physics from Professor Kleppner, in particular, Kleppner's laws. Have any of you ever heard of Kleppner's laws? Dan wrote a book that was used for freshman physics, and that class was called 8.021, kind of an MIT geeky way of calling classes, and it was in a book authored by Kleppner and Kalinko. And on a handout from that class at MIT were Kleppner's laws that said, angles that look equal are equal. Haven't you always used that when you're doing mechanics problems? Always make an even number of sign mistakes. This is really important stuff. If you know a solution, you can probably find it. You know, I mean, we learned that in our differential equations classes. The force is proportional to the displacement as long as it is. Yes, that definitely goes a long way in experimental physics. And a better name for the law of gravitation is the law of gravitation. Very important stuff. That's from freshman physics. But here's Kleppner's law version 2, which I learned in graduate school and have applied for the last 30 years of professional work. It's also known as the most important lesson in experimental physics. Mike Cash and I learned this from Dan. Any knob should be turned until just before it stops helping. And that's really important. You turn every knob in your experiment, but don't go too far. You want to stop just before it stops helping. And do that with every knob you've got, and you will definitely win in your experiment. So thank you for your attention, and thank you, Dan, for everything, in particular for the privilege of having a career in physics, which I would not have had it not been for you.
So my question is about the interferometric trick to get rid of the background, so you could pick out the lines cleanly. And you began by saying, well, these lines are not these cars lines are not where the Raman lines would be because of the background is shifting the peaks around. And what I'm wondering is, when you apply these tricks to get rid of the background, is there a residual shift in the line? If you were trying to make a precise measurement of where the line is, would you make a systematic error because of this cancellation thing, or is it clean?
I'm not aware of any reason it wouldn't be clean. But keep in mind, it's not meant for precision measurement per se. If you were wanting to do precision measurement, you would do Raman and just take the hit in signal, live with it, because then you wouldn't have anything to worry about. You use cars when you need a lot more signal. Raman is going to always be, it's going to be beautiful, but cars has a huge amount of amplification. And usually people just live with the distortion and say, well, I know that the center of the line is somewhere within its width. I'm not going to split it too much. And what I've shown is you can get a line, and the signal to noise is 10 or so you can split it by 10. I think you could trust the technique there. Whether or not there's some shift that might be metrologically significant if you were really pushing it, I'm not aware of one, Bill. If you look at the equations, it's not there. The equations just give you the imaginary part of the Raman susceptibility. But I have to admit I'm not a theorist, so I haven't looked for some higher order correction.
So maybe we should get going. Let's thank Professor Welch again.
Thank you.